taking a region and basing a volume on a region, whether we're stacking something on it or rotating it, we need the functions that define the boundaries of the region, right? So here you got to come up with that function. So let's draw it. I'm going to go fast. 3, 0, and 0, 2, and 0, 0. Okay, so here's our region like this. So what is that? Well, looks like y equals negative 2/3 x. So you get the rate of change by doing change in y over change in x. And then you've got the y-intercept, so just plus 2. So you can just do that. Negative 2/3 x plus 2. And we're going to stack semicircles perpendicular to the y-axis, okay? So those are going to be parallel to the y-axis, x-axis. So they're going to go like, they're going to be sticking out at you, something like this. Semicircular discs. So the biggest one will be at the bottom here, and then they'll get smaller and smaller, and there'll be a real, like a tiny one here. The biggest one will be here on the x-axis. So we're just going to stack those up. So we want the volume of a typical, what is it, half semicircle, half disk, HD. Volume of a typical half disk will be 1/2 pi r squared h. Okay, so what will the radius be? So the radius of our disk, how could we relate that to x, y, change in x or change in y, the radius of our disk? And what is the base? Is the base an x, y, change in x or change in y? Just x, right? So the radius is really just 2x. No. 2x is the diameter. 2x is the diameter of the disk. X is the diameter of the disk. So therefore, right, so the radius is half of x. Now do I have it? Yeah, so the radius, you see the radius is half of x. X is the whole diameter, so the radius is half of x. And the height would be this little thickness, which would be what? Delta y. So we got 1/2 pi times 1/2 x squared delta y, and then we need x in terms of y. So I can use my equation and solve for x. Y minus 2. Negative 3/2 times y minus 2. And that's all squared, delta y. So that's our typical half disk. And then we're going to have all those from what to what? The first half disk is at y equals 0. The last one's at 2. So we're going to integrate all our little half disks from 0 to 2. Questions on this one? Here's your chance. Question? Okay, let's look at one from the most recent assignment, or the second one. So again, this is x. Which I'm getting from there. Okay. Next one. 14. No, 16. Strings and chains. Do the fifth. High success. So I think we'll just press on to new stuff, and he'll take a few questions or do one more example maybe. Which one is the? Actually, I do want to talk about that one. What is that one? Nope. The one about lifting the chain up. 6. So this one, there's a different approach to this, which I think is worth mentioning. And so there's kind of two different approaches you can use. One is more consistent with how we did the lifting the like the chains and the buckets. So, but it's still different. So you could say, you know, as you're lifting this bottom link up to the top, you have a typical situation like this, and so you'd be looking at the weight of that, which is the force to lift it, times a little change in x. And so you get your work. This would be kind of consistent with to the examples what we did on. It's a different situation. You have to kind of look at things differently, but it's the way that you set up a little bit of work is consistent with how we did it last time, which would be the work. A little bit of work would be the force times a little change in distance. Okay, and so as you're pulling up, it's going to get heavier because you're going to get more and more chain as you're pulling up. So you got to figure out what your force is as a function of x, right? That's going to be a function of x. But I want to talk about a different way to approach this. And another way to approach this is we look at, instead of force times a little distance, we can look at, so here's our chain hanging down like this. We can think about the fact that we're only going to be really doing work on the bottom half of the chain. Do you see that? And so if we pick, say, a little bit of that down here, we can just analyze a little bit of force, right? So a little bit of the weight of the chain. And then where's that going to end up? That's going to end up symmetric up here, symmetric across this line. So in the end, it's going to end up about here. So now, instead of the distance being a little distance, we're going to take a little bit of weight and we're going to move it this distance here. And so then we're going to do that for every little bit of weight, starting at the bottom up to the halfway point. So if we made x down here from the center point like this, then what distance does the little bit of chain have to go? It's going to go 2x, right? So if a little bit of work equals force times distance, so our force is going to be, we're going to do that in a second, so a little bit of the weight of the chain times the distance will be 2x. Okay, and so then a little bit of force is going to be what? The weight of a little bit of chain. And so this is it's going to be 2.5 pounds per foot, right? 25 pounds over 10 feet. So this chain weighs 2.5 pounds per foot. And I'm going to take delta x feet of chain, meaning a little bit of chain. So what is the weight of delta x feet of chain if the chain is 2.5 pounds per foot? 2.5 delta x, right? What does a constant rate of chain mean? Given any change in x, the change in weight is 2.5 times the change. Remember talking about that first couple days? All right, so it's just a constant rate. So given any change in feet, the change in pounds would be the product of those two. All right, so then times 2x. And then I'm going to integrate that. Total work is going to integrate from 0 to 5. Right, so the first little bit I'm going to need is x equals 0. The last I'm going to need is 5. So all these bits of chain, 0 to 5, going up a distance of 2x. 2.5, 2x. So I just wanted to show you setting up the little bit of work here was different. Rather than the little bit being a little bit of distance, now it's a little bit of weight, and our distance is, you take that, how far is that little bit of weight going? In this case, 2x. Okay, questions on that? Okay, let's do some more stuff here. New stuff. We're going to empty some tanks today. And you say? Tanks a lot. Or not. All right. So we're removing fluid from a tank. So the first thing we want to know is often it's water that we're trying to remove from something. And so we want to know the density of water. So in metric, you could be given the mass density. So this is the mass density. And remember, to get from mass to weight, or mass to force, what do? Right, multiply by 9.8. And this is only in metric system, right? Because mass, we need, so that's mass density, this is weight density. So therefore, the weight density of water is 9,800 newtons per meter cubed. Sorry, this is mass density, not just mass density. So make sure you, if you're doing a metric problem, make sure you're aware of what you're given. Are you given mass and need to find weight, or are you just given the weight? Now, when you're, like we said before in English, it's just weight density, right? So we don't really deal with mass in English units. Normally we just have weight to start with. So there's no multiplying by the gravitational constant, okay? Okay, so then the total weight of an amount of water would be what? So it's 62.5 pounds per foot cubed. That's a constant rate of change. Given any amount of volume, how much does it weigh? 62.5 times as much as that volume, right? So the weight of any amount of water is 62.5 times the volume of water, or 9,800 if you're in metric. All right, so let's look at an example. It says a circular above ground pool has a diameter of 20 feet and a depth of 4 feet and is filled with chocolate milk, which has a density of 64.3 pounds per foot cubed. How much work is required to remove all the chocolate milk from the pool? All right, so I'm going to do blue chocolate milk. I don't have a brown color here. Okay, so so we know that we're asking how much work is required. So work is force times distance, okay? So and force in this case is, what are we talking about when we're talking about force? Weight, right? So can we just get the weight of all the chocolate milk times the depth is 4 feet times 4? What's that? Okay, so that what I said would be, he's saying what I said would be as if all of it was at the bottom, but it's all at different levels, right? So why isn't this straightforward like that? Why can't we just get total weight and multiply by a distance? No, we're gonna get it. We're gonna get it out the top first of all. So first of all, let's make sure. So when we're saying remove it from the pool, we're gonna have to get all of it out over the edge, out the top. That's what we're saying. So why would this not be a straightforward problem? Why does this take more thought than just total weight? Yeah, and that's the same kind of thing he was saying, right? So exactly. So at the top of the pool, that water near the top of the pool is going to take less work to get out than the work at the bottom because there's less of a distance to go, right? So we know that we want to get, what, a typical amount of work. So remember, always our typical amount of whatever is something that we can calculate without having variation, right? So what kind of element are we going to have that we can actually calculate an amount of work for, right? So what will it be like when we do a typical amount of work of what? Something we know we can actually get a value of work for. Okay, what's that? It's just a disk from one level, a pancake. So right, because in one level, all of that fluid at one particular level has to go the same distance. Because it all has to go the same distance, now we can figure out the work for that. So it's going to be the work for a pancake of water, right? And we'll use the frame. So we'll use this frame reference here like this. X. Okay, so the work is force times distance. So what will the force for this typical First of all, what's the distance we're going to move our typical pancake of water or chocolate milk? It's going to be x, right? That's easy. So then what is the force associated with a typical pancake? That's the volume. So there's the volume. So when we talk about the force for a typical pancake, what are we really talking about? It's weight, right? So we're asking about what's the weight of the pancake. So the weight of something is the force needed to lift it, right? So the weight of something is the same as the force needed to lift it. So, right. So we're going to use this principle here that we've got the density, the weight density. So all we need is the volume of it, and we got the weight of it. So 64.3 times the volume that Zoe said, pi r squared h. Now we just got to figure out what these things are. What is r? Diameter of 20, radius of 10. Good. H is height. Delta x. And then x is now the distance that weight that we're going to apply that force, right? So the weight, we got to apply that amount of force to lift it over a distance of x. So that gives us work. Okay, and then we got our setup for the work for one pancake of water. So now we're ready to do total work to drain. Equal to integral from 0 to 4. So it's the whole thing's filled. So we're going to start at x equals 0 and go to 4. And of 64.3 pi times . Okay, so now in this case, unlike the lifting the chain up at the top of the building, there's really no like order in which we're going to do this. Like in that case, we started pulling. There was a distinct order to how things were going to happen when we're pulling. But here, it's just we think of all those layers separately and think about moving those layers out separately. So we're just going to start with the top layer and then go to the bottom layer, and so that's 0 to 4. And the work that you do it's going to be a positive value. So for the ones like this, we don't really have that issue of direction. There's direction really, it doesn't play in this kind of problem, like the way it did when we were pulling the chain up. Questions on the setup for that? Okay, now suppose, as a variation, suppose that there was a pipe here, this, and it was a drain pipe, and say that's 5 feet. So maybe this is next to our block wall, and the total of the block wall is about 9 feet high, and we're going to dump all the water, the chocolate milk, into the alley. Okay, so we need this pipe that takes it up over the top of the wall, so it dumps into the alley. Okay, so then now how much work? Now how much work to get all this out? What would be different in the setup? Okay, so one way to do that would be to leave we could leave our reference point here as x. That's perfectly fine. So what we're going to find here in the next couple days is these problems are all about the frame of reference that you choose. And there are different frames of reference. And as long as you're consistent with the frame of reference that you choose, you'll get the same answer. So we could still keep our frame of reference at x equals 0 at the top of the tank. And then that's going to change the work for every layer, right? Then every layer would be, instead, the distance would go, instead of just going x, it would be going x plus 5. So that would be possibility 1, that so possibility 1 is leave frame of reference the same. Then our typical work of a pancake would be 64.3 pi r squared h, but then times x plus 5. So it's just same frame of reference. So we have the same layers from 0 to 5, but all those layers have 5 more feet to go. That'd be the first way to do that. How else could we do it? What would be another logical or another possible way? Yes, sir. Yeah.
Would we be changing the bounds on the integral, or leave that to?
No, because we're still, the bounds of the integrals are still referring to which layers we're going to empty. So if x is here, we're still emptying layers from x equals 0 to x equals 4. So it would be the same bounds. So yeah, that's good. We got to point that out. Bounds same, 0 to 4. Okay? Second possibility for this. How else could we approach this instead of what I just did there with the pipe? Yeah.
If you make the frame of reference the top of the pipe,
Right.
would your x be 9 minus x?
Okay, so now that's right. So another possibility would be make your frame of reference here. So now x would be this. Okay, and what about the typical work? How would it be different from the typical work we found the first time? Maybe 64. So we got still the same weight, and it's still moving a distance x. So now this would be the same. So this is change frame of reference to this one. Now this is x, all like this, and now this stays the same. The typical work for one layer of water is the same, but then what changes? But now the bounds are from, so if x is here, then our first layer is at, where's our first layer? X equals? Nope. First layer is x equals 5, right? So the pipe is 5 feet up. So at x equals 5, we got our first layer. 5, 2. The last layer is x equals 9, right? But the way we set up, the typical amount of work for the layer, for the pancake, is the same. So we get to more complicated problems. We're have this frame of reference issue. It's usually like a trade-off. Like, so choosing a certain frame of reference will make your life easier in one aspect of the problem, but make it a little more complicated in another. So it's like a trade-off, but then sometimes we prefer a certain difficulty over here and a certain ease over here. So we look for the best kind of overall situation. Questions on this problem? Yeah? What's that? Then we wouldn't have to do any work at all. Because it would just leak out. Yeah, it's yeah. If there's a leak in the bottom, yeah. I mean, literally that's what happens. It just leaks out. So we don't have to do any work because we're not. Yeah. So it just flows down, and we're not actually taking the water up out. So the thing about work is the force to lift the force to lift it. So there'd be no force to lift anything. So other questions? Okay. Something. So here is a trough. Imagine so it's like horses come up and they drink water out of something like this. So I'm showing that the length this way is 200 centimeters. I didn't draw it all, so I'm just showing the end of it and then showing that it's that length is 200. And so we want to say how much work to empty this trough. So this was harder.
Is it top 100 or 180?
100. Almost made it better. Okay, 100. Okay, so how much work? This is just water in here. So we're going to choose our frame of reference. So I think the easiest frame of reference here is just to make it the top. So often like where you're getting the water to. Oh, sorry. So it's half filled by height, right? So the trough is half filled by height. So half meaning not half the volume, half as much volume, but half the height. Okay. So we're all on the same page because you guys are going to work on this yourself. Let's make our frame of reference from the top of the trough. If you haven't gotten it by now, so you have to take a horizontal slice in order for all the distance to be the same. If it's anything other than a horizontal slice, you can't calculate the work. Right? A horizontal slice all moves the same distance, so you're able to calculate the work. Any other kind of element that's not horizontal, you won't be able to calculate the work because it's going to move different distances. Does that make sense? So when you do a horizontal slice, you get rectangular. Okay, keep going. Yeah. I would recommend. It doesn't. Probably. But when you start multiplying them together, now you have centimeters squared and centimeters cubed. So I recommend doing it towards the beginning rather than the end. Point 2. Oh, 2 meters. Sorry. I was thinking 20 centimeters, right? There we go. Is that right? Thank you. It changes depending on what? X, right? So we've done that before, right? We've got the width depends on X. The width depends on X. Your expression is going to be a positive amount of work, so you're going to go around 0 to
Also, SCS. Yeah. Oh, because it changes. Yeah. Because that's. I lost it.
What's that? Negative 4/5? Is that right? I'm all in meters now. Everything's in meters. This is meters per meter. So if x is in meters, this is the width in meters. Okay. Questions? Okay, questions? Always. Force is weight. Force is always weight. Okay, so now you gave it a shot. I put up what I. So what's going on here? The width of your typical slice depends on x. So I threw some ordered pairs up there, and I did it all in meters. Okay, so I changed everything to meters. So when x is 0, that width is 1 meter, 100 centimeters. When x is half a meter at the bottom, the width is 0.6 meters. So those are those points. That gives me a rate of change of -4/5. And then this is, I've got, because I have a 0 point, I can just throw on the y-intercept there, -4/5 x plus 1. So that's my width. So then length is 2, width is my dependency on x, my linear function. Delta x is the little height of my strip, so that's my volume there, times the weight density is my force, or my weight of the strip, times x is how far it has to go, gives me work. And I'm going to add up all those typical bits of work from 0.25, it's half by height, so from 0.25 to 0.5. And that'll give me the total work to get that water out of the trough. Ask on your way out. Oh, yeah, go ahead.
Are you able to do an integral from 0 to 0.25?
Yes, if you change your frame of reference to here. So if you put your frame of reference there, that's fine. But then the distance it has to go,
Should be 60
x plus 0.25. The distance in this thing, instead of just x, you'll have x plus 0.25.
Also, your width function.
And you'll have a different width function. You'll have different ordered pairs.
The 0.5 and 0 would be
-4/5 x plus 0.5. I don't know. 0.3.
4/5
Point.
y plus 0.5. So, yes.
I can't. Okay. All right. Happy Wednesday.
So, I have a couple things.
I would say that.
So from the other day, doing 1D problems, like string that you lift up by the end, bring it up. I can do 2 different reference frames where you look at the piece of the chain and you lift it all the way up, or with incremental displacement instead. So like d equals delta x.
With
or the
increasing
mass
length,
of the-
increasing weight.
So I can do
But-
either of those.
So I did that.
Right. Did you do this one? You did this one.
No, I talked about both of them, but I actually set up the incremental weight traveling the long distance.
Okay, so I won't do that one. And then I could do a rectangular prism that's pumped out to the top, a hemisphere where it's pumped out to the side. And I was thinking the inverted cone with a variable height.
Yeah. So the thing is, like all of those are Weber problems, but that's okay.
Yeah,
Yes.
I was thinking I'd have them do it generally
Just let's do something
rather than with numbers.
that, but something that's circular. So yeah, like you could, like a punch bowl. Punch bowl would be good because that's harder because the function is now not linear, but it's
Yeah. Yeah.
and then you get a weirder integral.
Okay.
So yes, the punch bowl is good. Or circular trough, like it's just like a
Yeah.
semicircle trough, like this one, the trough that extends back.
Okay.
Yeah. Yeah.
I just want to see if you could help me clarify. I'm having some trouble thinking about force, like in different senses, like newtons and pounds per.
Yeah, that's really
things like that.
important. That you